पहुंच गया।
हाँ हाँ जी। Uh, Hi, thank you for joining for today's session. I hope I'm audible. Yes. Yeah, sorry for preponing this session. Uh, yeah. So yeah. So let's just start with today's session, and then since this is going to be the last session, that I would be, you know, helping you with some of the topics in this course. If you have any clarifications or doubts, feel free to ask me here. Okay. Yeah, let me just start the screen share. Yes. I hope the screen is visible. Uh, yeah, let's just start uh, today's session. Yeah, thank you for joining for another session of conservation geography. So let's just go over the week 11 assignment questions. So Oxford can be categorized as mining town, garrison town, educational town, or religious town. We all know that Oxford, from the Oxford University, and so it is an educational town since it's based around that place. And New Delhi can be categorized as a what sort of town? Administrative, industrial, transport, and commercial. So since it's the capital of India, so it is an administrative town. Similarly, Vishakhapatnam, which is a city in coastal Andhra Pradesh, can be categorized as administrative, industrial, transport, or commercial. It's a transport town because it has one of those major shipping ports on the eastern coast of India. And similarly, Varanasi is a religious town. And going ahead, which of these is a factor governing barrier effects of roads? So, so in the last week we were discussing, right? Uh, so what all things that act as a barrier for species to cross the road? Whether it is traffic intensity, the speed of vehicles, driver sensitivity, all of the above. So it's all of the above because traffic intensity is what we had discussed earlier. The more the greater the amount of vehicles on the road, the more it's going to have a barrier effect on the animals. Similarly, the speed of the vehicles, the faster or slow depending on the species, it can act as a barrier. Similarly, driver sensitivity. So some regions or some people uh, are insensitive about a lot of other animals. When you're going through a protected area, although there are signs saying speed limit is 20 to 30 kilometers per hour, these insensitive drivers will be like zooming past this road at like 80 90 kilometers per hour. So here the driver sensitivity is also acts as a barrier. So even there is very little traffic, but if the driver is like, yeah, I don't care if I hit a deer and it dies, I don't care. If that's how the mentality of a driver is, so he can act as a barrier or induce the barrier effect. And the ability to produce a good using fewer inputs than another producer is. So when you're making goods, so it's an absolute advantage where you are putting very few inputs. So which of these is or are examples of mitigation measures to mitigate impacts of linear infrastructure on wildlife? So what are if you remember last week we were discussing linear infrastructures, right? So it can be roads, railways, or any of these things that are pipelines that tend to be in straight line for most of the path. So which can be act as a mitigation measures. The underpasses, culverts, box culverts, pipe culverts, all of this. So it's all of this because we are discussing bridge and underpasses where you have flyovers, and then the underpass can be used by animals freely to move from one place to another. And then the culverts, so there are different types of culverts. It can be box culverts for larger animals. Pipe culverts can be for smaller mammals and amphibians and reptiles, or even insects. So all of these. And then bilai can be categorized as in, so bilai, if you know, it has there is a steel plant. So that's an industry. So the town that has settled around bilai is mostly an industrial town. Similarly, Singrauli, it's a mining town. So it's famous for mine, where a lot of mines are there. So it's a mining town. And then the price of a good that prevails in the world market for that good is the definition of. So whatever the price of the specific item that is being sold is across the whole world. So it's the world price of the specific goods. Yeah. So yes, that's the previous week's assignment questions. So we will. So if you don't have any clarifications or doubts, we'll slightly go ahead and uh, go into trying to look at some of the topics from this week. Okay. Since there are no doubts or clarifications, so we'll go slightly ahead and then try to understand uh, remote sense, few concepts of remote sensing and GIS. And in the end, I'm also thinking of discussing one major hot topic of renewable energy, how it can impact the environment and wildlife and people. So let's go ahead at remote sensing, right? Remote sensing uh, is just, if you want to break it down literally, it's remote sensing, sensing things remotely. But so so it is acquiring information from distance. So the information can be what all different things are, or how a specific thing is. For instance, uh, if you see this graphic image that you are seeing, most so when you look out for uh, news articles, or when you have come across in the news that so and so exoplanet is discovered, so, like Earth like planet is discovered in so and so area, or there's some planet so and so light years, so many light years away has at like atmosphere or water in it, or frozen state, some sort of news. So most of it is done by remote sensing, right? Because you can't actually travel that far to actually go and test whether it is there or not. So those are done by either Earth-based systems, like as you can see here, or systems that are based outside Earth, especially in the Earth's orbit. Mostly in the Earth's orbit. So there you are trying to gather information. So if a person is if a scientist is interested in trying to find out extraterrestrial life forms, so he'll be looking out for signs that actually resembles life, right? Or planet that has water, so they will be looking out for some signs that says, look, this is what water looks like. And then, so how do they do that? So it's mostly recording reflected or emitted energy using sensors on satellites and aircraft. So mostly it is satellites, and then there are few aircraft specifically, sometimes specifically designed to gather this information, right? uh, yeah. So this is how, this is a graphic image of how a satellite can be actually gathering information. So there are the multiple ways which slightly go and discuss them. So before we go ahead, let's just look at different things. Orbits. So if you remember, a lot of these uh, satellites that we put out in the space actually had to revolve around the Earth. They had their own orbits, right? And there are different types of orbits each satellite can have. The one is a geostationary orbit. Uh, so, so a geostationary orbit is the satellite has an orbit of its own, but it will be going around Earth, but it is kind of stationary at a specific location. So, for instance, India sends a satellite, and then it wants to monitor specific patch of Himalayas. Let's say they're planning to study glaciers, how they are changing over time, or they are melting over time. So this satellite will be stationed at a specific region for most of its lifetime there, and then it will be rotating, going on around Earth in that specific orbit it's only, and then it will be focused solely gathering data from a specific region. And then if you look from Earth, it looks like as if it's stationary because it's constantly pointed towards a direction. So those type of orbits for satellites are geostationary orbits. And then there are low Earth orbits, mid Earth orbits. So they generally vary in terms of distance, but these satellites kind of go around the Earth, right, in a specific manner. So if and then similarly there is polar orbit and sun synchronous orbit. So here the satellite kinds of goes close to the pole. So polar, it goes through the polar regions and it orbits the Earth, and in the process capturing you know the whatever it's supposed to, right? So there are different types of orbit, and then based on different applications, different types of satellites are put into different sets of orbits. And most of the satellites that are actually used for remote sensing depends on what purpose. Mostly will be in the low Earth orbit and polar orbits, but if you have a specific targeted region, then it might be in geostationary orbit also. And yeah, little bit of physics back to, because we're trying to understand, if you look at remote sensing, we are actually measuring the reflected or emitted energy, right? So what spectrum of energy, because in the most of the energy that we receive is from sun, right? And then it goes from 10 to the power of 6 hertz to 10 to the power of 21 hertz. So like radio waves to gamma waves. The shortest of the waves is gamma waves that have a lot more energy, and the longest waves are the radio waves. They have lesser form of energy. And then UV rays, radio waves, microwaves, infrared, and visible light. So visible light is what we actually see, which is very little, right? And then we have ultraviolet, then X-rays, and then gamma rays. So sun emits most of these rays, but we are able to see this spectrum, the very narrow spectrum. We use radio waves for communications, especially mostly radios, and then mobile phone, and then Wi-Fi. And then we have microwaves, mostly for, because they carry a lot of heat also. We use them for heating our food, main microwave oven. uh, and then we have infrared rays that we majorly use to communicate in on short distances, like TV remotes or AC remotes. And then the visible light, and then the UV light. So it's out of our visible range, but it has much more higher energy. And then we have X-rays. So we use these X-rays to actually, for a lot of medical reasons, medical purposes. And then we have gamma rays, and then there. So each of these light, that most of the light that is actually coming onto Earth is reflected. So each object and each body has its own absorbance and reflectance. And then, for instance, if you see what are colors, So it's nothing but what we see as colors is that particular range of this electromagnetic spectrum being reflected back. Especially colors is in the visible light region. If that particular spectrum is reflected back, we perceive it as that color, right? For instance, plants, so they reflect a lot of green light. They, most of them look like green, right? Because they absorb most of the light and then reflect back the green radiation part of it. So similarly, there are a lot of objects that absorb and then reflect certain regions of light much more prominently than others. So we try to exploit that aspect, that certain regions are well reflected by certain characteristics, and then we try to use that to do remote sensing, right? For instance, as we are just looking at plants, right? So the certain wavelength they reflect much more better, and then certain they absorb. So if we can manage to find that specific wavelength, we can map actually where all the trees are and where all forests are. Similarly, built up area, like if it absorbs light in the infrared region, so a lot of these built up buildings, if they absorb, so we can have a particular sensor that can actually measure infrared emittance. So if, where all the infrared radiation that is being captured by the satellite is exceptionally low, we know that because these built up areas absorb a lot of this infrared radiation or emit a lot of this infrared radiation, then it has to be built up area, like in contrary to other regions. So that's how we do this. And then let's just look at what all different wavelengths that common structures actually do. So snow and ice, so some objects have a peak emittance or peak absorption, where they actually peak at certain wavelengths, and in some they might have multiple. For instance, snow and ice, so they have a specific spectral signature, so that is around 600 nanometers, while broadleaf and needle-leaf vegetation 800 nanometers. So percent reflectance and what's the nanometer. Similarly, different types of soils, different types of water, so whether it's clean water or turbid water, just finding out water itself, right? So we use these signatures of specific items, and then once we have those image of a spectral image of an area, so when we actually send these satellites to when you that will be used for remote sensing, so the purpose is first decided, and then what all sensors it is going to carry is decided based on its purpose. So if its purpose is for for monitoring snow and ice, then they will make sure that that satellite has majorly at least this sensor, its sensor is functional, this sensor is present, and then other priority will come up. So once we have those images, we know the spectral signature of this item, and then we try to run those images and process them and try to see how those things are changing, like for instance snow and ice here. So most of these sensors can be two types. So there are active sensors and there are passive sensors. So most of the remote sensing that we actually do from space is passive sensors mostly. Because we use the energy that is being sent out from sun, and then earth reflecting that energy, and then those sensors are actually just are there to just to measure that thing. Well, active sensors, they had to actively shoot some sort of you know radiation towards the surface, and then that is specifically targeted, and then once it is reflected back is red, and then that's how we have that information. Okay, so based on these measures, they vary. Like, for instance, our remote sensing, for instance, uh, the maps, all these for land use land cover maps that we get is through passive sensors. For instance, and the other lidar uh, is in those are actually active sensors, because you are actually actively emitting radiation, like the laser beam that emits infrared radiation, and then you actually measure what is actually coming back from the surface, right? So that's the difference between active and passive. Mostly we use passive, but these days we are using actively much more, because you have better control of, the specific spectrum that you want to actually capture. And then then there is a concept of resolution. So the resolution is like how fine is your data or how coarse is your data. So depending on different different work people are doing, especially scientists who will be using a lot of this data, or policymakers, uh, the resolution actually varies. So for instance, you're trying to look at how, you know uh, the if you're looking at a protected area boundary, right? uh, and then how the number of houses have actually changed, or the our built up area has changed around this protected area, right? Then you need very fine data, right? So number of buildings that have come up, number of trees that have been cut down, so and so. So there you might need very fine scale data. But if you are trying to look at uh, other ways, like let's say, yeah, snow cover, so you might not need resolution of that fine scale, because when there is snow, it's huge, and then you can easily track it, right? So then you can have, slightly relaxation in terms of how coarse or how fine your data can be. So it depends on what actually is your purpose. So when you look at the resolution in terms of this remote sensing information that we actually get, it's the so most of these are images, right? What we get is an image. So here the resolution is the resolution of a pixel. So what does the uh, length and width of the pixel is, or the in terms of when you put it onto the ground, so what does each pixel can capture. So the highest resolution imagery that we have available for all this analysis is 10 by 10. And then the older resolutions that we used to have was 30 by 30 meters. Okay. And then there are different set of satellites that were actually doing. So the older satellites, generation of satellites that actually did this 30 by 30 meter resolution was Landsat. And then nowadays, 10 by 10 meters, this is a new set of satellites that has been recently put up that actually captures 10 by 10 meter resolution. But so the area that you are going to get is less, or if you have higher resolution, you should have a greater machine power to actually able to process that data. And then if you're trying to look at how things have changed across larger areas, then you don't have to worry about that fine scale resolution. Your resolution can be 30 kilometers by 30 kilometers, so on. And then so let's just look at how that resolution actually transfers into. Okay. So if it is the same image photographed at different resolution, so if the resolution is 30 meters by 30 meters per pixel, so but that means each pixel has an information of 30 meters by 30 meter area. So this is what you get on the leftmost side. So if it's 100-meter area, you are seeing some jittering. So it's not you can't make it out much, but it might be what some people need compared to others. And then 300 meters per pixel. So this is how it looks. So you can't actually make out some of those specific land features at coarser resolutions, or when the resolution is very low. When at higher resolution, you can actually make out structures. Here, as you can see, there are roads, there are buildings, there are vegetation. But here you can slightly make, but here you can hardly make. What is there? What is the information being captured by in pixels? So there is a trade-off depending on what you want to do and what sort of resolution you need. So this is spatial resolution, basically the resolution in terms of space. And then there is another resolution called temporal resolution. So if you have photographed the same place at the same resolution, so don't worry about the spatial resolution, like across months, like May, June, July, August, 4 months, and then you are seeing how things have changed across time. It can be time of, it can be single week, or it can be a year, across years also. So that is called temporal resolution. So if you go back to the earlier example we are discussing, that if you want to look at how many new built up areas have come up across around a protected area, then you need temporal resolution along with good spatial resolution. Means you need data across multiple years, and to see how, let's say for instance the protected area was delineated in, say, 2010, and you want to see 2024, how much built up area has come up. So across 14 years you try to look out for at least an year. That's a reasonable time frame we can think of. New places can be added. If you have much more finer data, you can also look at like every month, but the reasonable time resolution is what we choose. And then across years we see how the built up area is actually going. And then how do we do that? So we don't know what is here we can make it out, but when you want to tell the system that this is what a building looks like, this is what vegetatory looks like, this is what a water body looks like, because what a system can actually, or a computer can actually understand, is uh, digits, right? Mostly in terms of numbers. So how do we translate this thing into numbers? So it's simple. So most of these images have pixel values, right? RGB is what we get to see, or mostly in the visible region. So once we put up sensors on top of satellites, and when we capture the photo, so each pixel, or these values are by defaultly uh, gathered by that sensor on that satellite or whatever device it is. So we have for each pixel different values. For it can be, based on the sensor. If it has RGB sensor, the value for R, red's red, the value for green, the value for blue. If there is infrared sensor, the infrared, there are multiple bands also, infrared band 1, so on, or ultraviolet. So what's the value of the specific pixel? So its corresponding pixel, and then these values are by default recorded. Okay, so once we have that values, and then from a, from what you can actually see, you say that, this is a building. Let's say if you zoom in on and say this pixel is a building, then you train that model saying that, if you have these values of, RGB, and then infrared in so and so range, then it is a building. If the range is different, then it is water, then, or else it's something else. And then you train it saying that, like, and then you ask it to classify, say, and then do this for all of the whole image and give me the value. Then it what it does is it classifies that thing and then gives us a map. So to ease that, so what we sometimes use is as false color composites. So this is what true color according to us looks like of a area. When we put, false colors, so instead of allotting red band to red band, we allot red band to other band, like it can be green, and then green band to blue band, and then you will get a different color compo. So what it should actually look to us. So that makes us, a little bit easy to interpret. Once we do that, we allot these values saying that, this is built up area, this is vegetation, this is barren area, this is water, this is so ice, this is so on, so on. And then once you classify it, this is what you get as, it's a called, so land use land cover map, because you're trying to understand what are different land use in that area are. So if you look at this map of India, it's like across 10 years, so they have done this work. And then so This is what it looks like. In the Western Ghats region, you have a lot of evergreen forests and then mixed forests, while you have a lot of water bodies around here, right? And then you have a lot of barren land and then snow and ice around this area. And you have a lot of cropland, and then you have a lot of built up sorry, yeah, it's shown in red, right? So these are classified based on those pixel values. So just for you have to train it initially saying that this is how this each land use looks like, then and you ask it to run it. Depending on the resolution, you will get it. So if you have a really fine resolution data when you are planning to do such a job for whole country, then it's going to be a huge task. So the resolution can be scaled down because the fine scale resolution might not matter here much. But if you want to look at specifically in and around Delhi, then it might matter. The resolution, spatial resolution, especially. Okay, so that's where that's what we do mostly after capturing that information, remote sensing. So once you get those images that are captured, we had to process them. So that's how this processing is done. So depending on different purposes, if the purpose is to look at how the land use has changed across years, that's what we do. So we say this is this specific land use from satellite imagery, and then we ask it to you know classify the whole image based on these values, and then it will do it, and then what you get is a final map. Similarly, you can use remote sensing for a lot of other purposes. So for mapping rivers, you know uh, uh, to track a lot of other things, right? uh, we'll slightly move ahead and then go out of remote sensing, try to understand other thing. GPS. So it's a other thing that is not exactly remote sensing, but it's a common thing that we use in a lot of day to day life. If you have to navigate, a lot of us use Google Maps because we have you turn on the location, use Google Maps, say I want to go from you know so and so place to so and so place. Let's say, for instance, you want to go from Nizamuddin to uh, New Delhi, right? So you say, show me the path. So it shows this is the path, and then when you are actually traveling, it actually shows that you are here, you are currently here, you are moving at this speed, and then you are about to reach so and so. All this information is showing. So it is already possible because of this thing called GPS. It's global positioning system. So how does it actually works? So GPS is nothing but it's a space based radio navigation system. Basically your device emits some sort of radio signals that actually reach the satellites that are actually tasked with getting the GPS, and then sends back the information, and then you try to locate yourself where you are actually. And there are lot of different set of satellites, so it can't be done by single satellite due to errors. So to minimize that, there are multiple satellites that actually do that, and there are a lot of satellite systems that are put in place so that anybody can access that thing for any across the globe. So Navstar is popular, uh, and then made by US. It's a US based satellite system for GPS, and GLONASS, and then Galileo. So these are Europe. GLONASS is Russian satellites, and then Galileo is a European system. And then there are lot of other systems also. And then the major principle that GPS actually uses is called as triangulation method. So what is that triangulation? So when you have a GPS receiver, so before mobile phones actually became the way to navigate, we used to have these things called GPS devices, and then we still have them we still use them for accurate navigation in a lot of these places. Even when we do field research, we actually carry a GPS device, mostly made by company called Garmin, but there are other companies also, I think. So so what does it do? It has its own, it acts as a receiver. So it actually measures the time taken for the radio signal from that receiver that we are holding to go to the satellite and then actually reach back to you. Okay, it might take very less, it can take, less than a tenth of a second because of the speed at which these waves travel, right? So then it multiplies the time by the speed of the radio wave. So we use radio waves for this navigation, and then to obtain the corresponding distance between it and the satellite. So it does the calculation, say it calculates the distance between you and the satellite. Once it has done that, and then it puts that receiver on some sort of an imaginary sphere. We know that Earth is a sphere. It's not a perfect sphere, but it's a sphere. So it puts us somewhere on that sphere. Let's just say this satellite has put us somewhere on this point, right? And then similarly, and then this signal goes to another three set of satellites. So it's like we have at least four satellites trying to kind of triangulate our location. So they do that same thing. So the radio is emitted to the satellite, it comes back, calculates the distance, and put us on a sphere, and then that's where we go. And then once we are there, so once you get all those information onto the receiver that we are holding, so it uses that to calculate our latitude, longitude, and altitude. So we use at least three, generally four, to accurately measure that location to minimize the error. So so a lot of these GPS systems that we use are actually free, but although they have been built up for military purposes, the civilian way that we use these days is actually free. But they have this slight error associated with it. So even if you look at uh, these mobiles, right, if you are inside your house and you want to actually navigate, it shows a blue area in Google Maps at least. That this is the error area that I think I am you are in, but I'm not sure which place exactly you are in. So that is because you're not able to effectively communicate with this set of satellites because you are inside a built up area, and then built up area are not great for much of this transmission and receiving. Once you go out in the open, you can do that, but still, to limit civilian use, there is slight error. Like sometimes the accuracy is up to 5 meters. So 5 meters means, so there is a circle. So the location that you are being shown, it's likely that you are somewhere in this 5 meter circle, or sometimes the resolution can be 3 meters or 10 meters depending on the device that you're using. So if you use these Garmin devices, the minimum you can get is 3 meters error rate or the precision. So yeah, and then they also use this for tracking. And similarly, and there are a lot of purposes. This GPS has a lot of other purposes, like be it for military use or be it for everyday transportation. And then a lot of times, aeroplanes, they actually use GPS based information to travel. And then we also use GPS based information for actually in wildlife monitoring. How? You might have known about or heard about radio tracking collars, right? So what do? So they have this. There are different types of radio collars. So one uh, is short range collars. They actually, you go into the field with an antenna. This is what you might have seen in a lot of images. So once you have that tracking collar or tracking device that has been set up on the animal and released, you actually go with an antenna and try to do the triangulation. So if the animal, let's say, it's sleeping around this area, right, and then you say that you started from here, and then you say the animal is in this direction. You move, couple of uh, meters. Let's say if you moved 500 meters to, and then chose a random direction. Let's say you go this way, you went this way, and then try to actually relocate it. You know, you now you figured out this is the direction, and then again you go to an, and then try to say, triangulated it, say that, from three different points, this is where you're trying to, that the animal is around here. Now you once you go and search the animal, it will be there if it has not moved at that last moment. So that's how earlier it used to be done for tracking animals. Once we had these GPS systems, what they actually do is a lot of these uh, collars or tags, they have these satellite receivers. So the ones that we are discussing, that we have on handheld or mobile devices, is actually packed inside that tracking device. Be it a collar that is used for mammals, or a backpack that is used for flying flying mammals or birds. What do? So they actually receive, they are solar charged. Most of them are solar charged. Once they receive, based on what you set up, they will receive the they will calculate the GPS signal, and then some have mobile sims associated with it. So they can actually transmit the data back once in a day to your mailbox, or to just message to you. So they actually use that thing to track animal movements. You can track them live, or you can have them, once in a day, just send me a GPS signal of where all have you been every 1 hour. So that's where it is used, especially for wildlife monitoring. And then in some regions where there is a lot of conflict, right? For instance, uh, in regions, if you have heard, in Tamil Nadu and Kerala, where there are a lot of tea plantations, and then there is a lot of associated conflict. So, a lot of non-governmental NGOs have set up these things, where you have no, what if an elephant is sighted, you try to report it, and then they try to monitor it regularly. So that requires active monitoring. But if you have, that this is a problematic elephant, or problematic group, or this group actually passes through these plantations, if you have one of those individuals collared, and then once you know that it has come close to human habitation, it triggers a message that, this elephant is nearby, specific elephant, just be careful around these areas. So it can also be used to avoid a human animal wildlife conflict. And then you also use GPS based studies to, actually understand animal behavior or biologies, be it, the home range, the minimum area required for the species, or where all that species actually moves in the landscape. Like for instance, if you have a protected area, right? And then this animal is staying very close to the boundary. When you tag it, you found that, most of the time it actually is using the human dominated area rather than the protected area. Then you know that, you have to take proper measures, that, to prevent further escalation of any sort of conflict between humans and these species. So that's where GPS based systems are being used for animals. And then earlier, these systems used to be very costly, because of the size, because of them being have to be imported from outside. But these days, because of powered pad solar powered uh, you know trackers, and then GSM based sim based GPS locations, we have uh, you know these tracking measures that have been, made much more easier. But it's not easy to track any random species. You have to get proper permits, and it's not really easy task. So that's where broadly these GPS systems are used in wildlife, and then wildlife management. And then the other form that we have is LiDAR. So this is a part of active sensing. If you remember, where here you are actually actively sending some sort of signals. That signals are actively received and then interpreted later on. So LiDAR It's nothing but light detection and ranging. It's a remote sensing method to determine the surface of Earth. It can be any surface. Mostly, since we use it on Earth, we just use it as a Earth. So, what are different things that it actually needs? It actually needs a GPS, and then so that and then it has to be connected to satellite to know actually the precise location that it is actually you know sensing it from, sending the laser pulse or interpreting the information from, and then a ground unit that can actually control all of these things. So mostly these days, GPS are widely used mostly on drones because the technology has gone, you know, much more accessible. The drone technology and the lidar, but it's not really common, at least in India. Earlier, they used to be used systems based on aircraft. So there will be aircraft that have been fitted with this sensor and then emitter, and then they used to fly that aircraft, and then the data is then gathered through the aircraft. But here these days, you fly a drone, and then you can just get the data of shorter areas, smaller areas. So how does it do? So we have this system that actually does that. It emits laser beams onto a specific area. So you set the frequency, the length of the area, the number of uh, times it has to repeat it, so on and so on. Once it emits, and then as we are saying, each property, each material can absorb and then reflect certain part. So and then it actually reflects, and then it actually gathers that whatever is reflected, the sensor sense it, and then process the data. So this is, and then this is what we get in some cases. So this is a delta region where the lidar has sensed, this is water channels, this is the depth profile, and so on and so on. Similarly, you can use it to sense forest structure because it gives a 3D map of the forest. You can actually slice it multiple times and then see what is going on inside the forest. Sometimes in some areas you will have very tall forest outside, from outside, but inside there is nothing there. So those things, if you had to look this through, you know a satellite, what you get is just a green patch saying that there are trees. Whether they are small, they are short, they are tall, it's not going to distinguish much. But through lidar you can say, this is there are some shorter trees, they're very shorter ones, there are taller ones. If you do cross section, you will get to see and if there is an understory or not, and then so on and so on. Yeah. So, and then there have been people, there have been groups, research groups that have actually studying different set of species in this forest. So, for instance, there are this group of woody climbers that you see in tropical forests called lianas. So, it's climbers that have huge, thick stems, right? So, they also act as a sort of proxy for disturbance because in some areas some species might be highly prevalent in disturbed areas versus some species are totally gone from those disturbed areas. So once you have this lidar data, once you cross section it, you can know that this species, this forest has good amount of lioness or so on and so. Similarly, there are studies that have been done to look at the effect of fires on forests using lidar sensors, because you get vertical stratification of the forest. Is basically you can get to see the cross section of the forest at any at any point in space. So you actually exploit that property and then try to see what actually happens to a forest when there is huge fires. Like smaller fires, the undergrowth might be affected, but in larger fires, the whole trees, the larger trees can also get affected. So those things you get to see much more clearly through lidar, rather than the conventional remote sensing. So that's why lidar is a popular technique that is being used widely in research field, and then they also use it in urban planning areas also. So for instance, if you look at this image, this is what a coastal town close to uh, No, no, close to sea ocean looks like, where most of the where the river is actually merging into the ocean. So you can also try to, using lidar, you can say, these areas are actually prone to, uh, likely prone to floods or inundation, so on and so on. Excuse me. Yeah? Yes, sorry. Yeah. So you can actually use those things to predict where all different things can happen, and then try to prevent uh, build up build up of your human interaction in those areas, so that you can prevent human loss or property losses. So, and then you can also build digital elevation models better, much more re- at much more higher resolutions. Digital elevation models are nothing but, so how does the elevation profile of an area looks like? Right, for instance, if you go to Manali, it's on a hilly, it's in the Himalayas, so it is much more higher. And then the regions around, if you map that, you can have a nice profile of how the elevation goes from here to there. So those things are better done through lidar, but it's a slightly expensive technology, and it's not that prevalent in India, at least as of now. So yeah. And then, yeah, that's all I have for uh, remote sensing and all. And then if you guys are interested, I can go ahead and try slightly talk about uh, solar energy, but that's up to you guys. But if you guys are not interested, I will stop, because this is the main thing that I wanted to deal here. Different aspects of remote sensing, and then where it can be actually used in terms of conservation or wildlife related things. So yeah, if you want me to deal slightly about solar energy, I can just briefly go over. Okay, yeah, thank you for responding. I will just go slightly touch upon. I'll try to discuss more in detail about how it can affect wildlife, because solar energy is a form of energy that has been documented as, or at least uh, s- told as, this is what we should do to prevent, uh, to reduce our, whatever impact, climate change impacts, right? I hope the screen is visible. Yes. So yeah, so just brief history of what is it. So it uses this thing called photovoltaics. It's a form of solar technology. It was discovered way early in the 19th century, 1839. So where, you know uh, Becquerel, Alexander Edmund Becquerel, discovered that, when he placed silver chloride in acidic solution and exposed it to sunlight, and then it generated electric current. So since the process of generating electricity directly from solar rays is called photovoltaic effects or photovoltaics. So that's what briefly has happened. And then later on, in around 1954, we started developing cells for, called photovoltaic cells, because after the growth of semiconductor and then those technologies, we had those enough technology to be able to harvest that energy, that using that photovoltaic effect to be able to generate electricity, right? So this is what a typical solar panel looks like. So there is a frame to support it, and there is a glass, and then there are solar cells. Just a sec. Yes, and there are these solar cells. That's what the blue things that we actually get to see, and then there is a junction board that actually connects whatever electricity is generated through the photovoltaic effects from these solar cells. So what does it does? So photovoltaic effect uses, uh, when the when the solar radiation actually hits the surface, it actually emits a lot of electrons, excites the electrons, and then it emits them. So it hits the solar cells, and then these electrons are excited, and then these electrons actually cause a movement, and then they are actually moved, and then movement of electrons is electricity. So they actually moves through that box, and then it's converted into DC form or AC form depending on whatever it is used, whatever is can be used. So each solar cell contains a semiconductor, mostly made up of silicon, right? So most of the solar energy that we use uses photovoltaic effect. So basically, use the photoelectric effect is basically this is the photoelectric effect where when the solar energy actually hits the surface of mostly the semiconductors here, it emits electrons. So we use that effect to generate electricity. Then you call PV or photovoltaic solar energy. We use solar energy for other purposes, for heating. So this is what we mostly use, solar heating. And and then we have other form of solar power, that is concentrated solar power. Here you don't actually use solar photovoltaic effect, but you just put up mirrors for so and so area, and then you have a large central tower. So these mirrors actually reflect light onto the central tower, and then these towers has the water supply to it, and then it actually generates steam boiling the water, and then that is used to run turbine. So here you are not at all using photovoltaic effect, but you are harvesting solar power. And then there are other futuristic forms that have been recently developed. So these building integrated photovoltaic. So a lot of these buildings, windows or the balconies have the integrated photovoltaic cells where a lot of sun can, when it hits, it generates electricity that can be used for building demands. And then space is always a demand for putting up large scale photo floating solar power panels, right? So most, if you have the solar panels on your house, if you have a huge house, then it can suffice for one person or that household. But if you're staying in an apartment, let's say for the instance, uh, the whatever the solar panels that can actually cover the roof might not be sufficient for all the houses, all the people that are living in the apartment complex. It can be just sufficient for two to three set of houses. So we need actually places that can actually generate huge amounts of electricity. So that's where solar power parks actually come in. And then there are different modifications to it also. So there are these floating solar parks. So where you have this actually solar panels floating on top of water bodies. So it has two uses. So it reduces water evaporation in regions where the water is a scarce commodity, and then you're actually using space effectively for generating solar power, because most of these areas where you have high intensity of solar power has associated uh, less amount of water to it, so mostly in drier areas. And then we have India has also largest uh, solar floating power plants across. So this one is in Telangana, and then we have agricultural PV. So a lot of these agriculture plants that we use actually have shaded. So once you shade that, you can use it to grow agriculture also. And then India is one of the fastest growing countries that is using solar. So if you look at the photovoltaic power potential, so so let's just break this term photovoltaic power. So what is that? So if you look at the effect that we use to photovoltaic effect to actually generate electricity from solar panels, right? So this actually calculates the power potential based on the photovoltaic effect. So basically, the greater the photovoltaic power potential, the greater the electricity generation that can be done using solar panels. So if you look across India, the drier regions of India, like western part of India, uh, central part of or the northern part of Karnataka, Andhra, and then we have Trans Himalayas, has one of the highest photovoltaic power potentials. So if you see here, all this is red. So this is Leh, and then uh, somewhere around this region is this is Spiti. So most of the Ladakh Spiti region has highest photovoltaic power potential, even in the Tibet region, right? And then, yeah, so just remember this region, right, that we are showing close to. So this is a huge lake called Somoriri that is in Ladakh, and then it's in this area called Changtang Wildlife Sanctuary. So if you just saw that, even in Spiti and Ladakh in India, these are the regions that are habituated by people, and then has higher amount of photovoltaic effect or power potential. So the government is actually planning to set up these huge uh, solar power solar parks to get that energy, and then use send that energy to the national power grid. But yeah, so the plans for Spiti has been cancelled, but the plans to build up a huge uh, solar park in Ladakh, close in this region where you're seeing actually red. So this is called Changtang region, and then it has been proposed, and then yeah, the work is going on. So we'll just go and try to understand that thing in a while. So how does it affect? So we know that it's the safest resource. The sun, sorry, the sun at least has a lot of energy to send, and it's a renewable resource at least for thousands of years to come. But the problem is the land for installation. Where are we going to put up? So we are always fighting for land. So we had to actually find land to affect, and then this land actually most of the times, if you look at this map, it's in the dry regions, and then these dry regions are arid habitats. So it can be deserts, mostly deserts. So here it's the cold desert in Ladakh and Spiti, while it's a hot desert in Rajasthan, right? And then these areas have, because it's a desert, it has one of those highest photovoltaic effect. So that's going to affect the native wildlife there, and then you're actually changing the land use. You're taking the land from one and then changing it to other. So because what used to be, you know pasture land or grazing land, or a scrub land, is actually now covered by all the solar panels. So there will be a shade associated with those solar panels, and the vegetation is going to change, and it has own effect. So you're actually changing the land, and then you're fragmenting the habitat, right? So these solar power parks are not going to be uh, a small uh, you know smaller areas. So they cover huge square kilometers. So they cover larger areas. So they actually essentially fragment habitats, and then the associated effects of fragmentation on wildlife is there. So we discussed it in the previous session. you know there are a lot of genetic flow, lot of other aspects that actually happen because of fragmentation. And there is a change in local climate. So because you're bringing a lot of shade, or because the temperatures are rising up so much, because you are concentrating all of these solar panels in a specific area, the temperature is going to rise up compared to other areas. So the climate is going to be much warmer, and then its consequential effects will be there. And then just to build those things, the disturbances that actually arise from just construction, it can take its toll. And then there is this thing called lake effects of large photovoltaic projects. So if you have these huge areas, so once you look it from higher above, and then it looks like it's a lake. So because it's so shiny and it's reflecting, a lot of these birds can mistake it for a lake and try to land in. Once they go and then try to land, that's it. Because the temperatures are so high, sometimes they can just burn, or they can injure themselves, and then that's it. And then if you look at uh, in terms of Ladakh, you know this region actually lies in a way major flyway. most of these birds actually migrate through this region that actually comes into the most of the Indian subcontinent. So this effect is going to be huge because most of these migratory birds are, some most of, not only, not all of them, most of them are birds that are, associated with water. They are, they can be ducks, or they can be some species of bird that are, that forage in and around water. So they are going to get affected by these lake effects, and then the land is gone, and then there are a lot of other effects they also face. And not only the wildlife part of it, there is human aspect of it, especially this region, the Changtang region. So the people that stay around here are nomadic herders. So they stay around in a settlement during the winter months, peak winter months. But during the major summer time, like, May to October, November, when there is the pastures are green, especially during the growing season, these guys will be going around and grazing their cattle. And one of the famous product that comes out of this is that pashmina wool from these, from these herders. So it's going to go. It has its own trademark, right? Pashmina wool is such a huge thing. And then, the wildlife. So there are species that are, unique to this region, like Tibetan wild ass, Tibetan gazelle, and then, yeah, they are going to get affected. Not only wildlife, the people and their livelihoods are at stake. When you have these huge scale of projects in these such, regions, such that are, affected by, that are going to get affected by climate change. Yeah. So are they really sustainable? That's the question we should ask ourselves. So solar energy, what we call as, renewable energy, source of energy, but the way we are approaching it, it's not sustainable form. I think we should be much more, uh, we should think a lot more about in that thing, and then try to deal with these issues. If you're interested, I would say try to go and read this article in scroll. Just say Ladakh or Changtang and solar power project. The first article that you get is going to be this, and then try to read. It has nice illustrations and then nice examples of how it is being done. And then, although the locals are opposing for that, but the government is still going ahead with the idea of building that power plant, solar plant, and then trying to connect it to the national grid. And most of that electricity that is going to be generated is not going to be used locally. It's going to be transported to Haryana and the rest of the country, so which is very sad. And then they are losing their livelihoods there. So yeah, the effects are going to be crazy. So so all this renewable energy, they have their own effects, but we are trying to put a, nice picture, paint a nice picture, and try not to look at the effects that it has on uh, wildlife, the environment, and the locals that are living in around those areas. Yeah. So that's all I have, yeah, for the solar energy part. So yeah. So do let me know if you have any questions or clarifications that you want me to go, because this is the final session that I would be interacting with you. And then this is because this is a 12 week 12. Yeah. And then I think you'll be having your exam soon also. Yeah. Yeah, glad that you don't have any doubts. And then I hope these sessions actually help you understand few of those topics little better, and then you got to learn some of those concepts. And then yeah, and then I wish you all the best for whoever is appearing for the exam. And yeah, if you have feedback, do put up the feedback, uh in the form, so that I can try to improve in the next sessions if I take them. Yeah. uh yeah, my area of research. So So I did my master's in wildlife science, and I'm doing currently a PhD student at IISc. I'm majorly working on ants, and then also looking at uh, plants and insects along an elevation. Especially, I'm currently working in Spiti. So yeah, that's why this jacket. It's really cold now since the temperatures have dropped down. So yeah, mostly work with insects and plants too. Yeah, I hope I could give some picture of how things happen in term, and then these sessions were really helpful to you guys. Okay, yeah. If you don't have any doubts or any questions, we'll end this session for today, and then yeah, that should be the end of these sessions. And if you're appearing for the exam, all the best to you guys. And then yeah, thank you for listening to these sessions patiently. Yeah, glad that some of these sessions were, you could get some of those insights. That's what I tried to put it up. Glad that you could get some of them. Yeah, thank you for the feedback. Yeah, chalo then, we'll stop here, and that should be the end of today's session. Chalo, bye.